Okay. Okay. Dear highly esteemed guests, John Waterhouse and Professor Richard Burke. And dear team captains and teams, we acknowledge you and your team's hard work. Thank you all for your time, whatever time of day you are in. The impetus for discussion of this concept of pre-cut vessel design and construction, like the impetus of all ideas, is based on speculation, curiosity, and memory. So I recall that on a World Bank sponsored mission to a remote and pristine part of Sumatra to Lake Toba, those of us in the mission saw firsthand the construction and operation of what had been pre-cut vessels. Each of the modern vessels carried hundreds of passengers and tens of vehicles. We learned they required 6 truckloads of parts, which were assembled on a sandy shore from which the finished vessels were launched. Very impressive. About the big question many of you team captains and team members are thinking and asking, will this webinar help in designing a safe, affordable ferry for the Niger River near Onitsha? The answer is, we don't know. None of us knows if it has any relevance or value to the situation of the design competition. What we do know is that getting insight into the process of design and construction of pre-cut vessels will serve you well in your professional careers as you address complex situations in remote locations, pristine locations, difficult terrain, and or with professionals of diverse capabilities. Segueing into professionals with diverse capabilities, with this outstanding professional careers, let me introduce our guests, our presenters and questioners. John Waterhouse is the principal and founder of Elliott Bay Design Group in Seattle. He has been engaged in complex vessel designs all over the world and is highly recognized as such. Professor Dr. Richard Burke, just newly retired from the State University of New York Maritime College, has had a career that has engaged him in many aspects of the maritime sector. Their CVs are attached to the note that I sent to you, and you will be amazed at their careers. By virtue of their dedication, experience, and intelligence, both John and Richard are highly recognized for their insights and their ability to communicate those insights. And now let me step back and ask Richard, would you like to begin? Thank you very much.
Well, good morning, and thank you for inviting me, Roberta.
Thank you.
This is a topic near and dear to my heart, and I think we're extraordinarily fortunate that John Waterhouse is available to discuss it with us. So I think, John, my understanding is you've prepared some materials for us to discuss. Why don't we start with you making your presentation, and then we'll go on to having a question and answer period.
Thank you, Richard. Let me go ahead and load the presentation. There we go. Let me see. Are you just seeing the
Yes,
presentation or are the notes also showing up?
The notes are showing up.
yes.
Notes are showing up.
And may I just say, if the anyone who's not, other than presenters, please mute yourselves. Thanks.
Try that again. Screen 2. Here we go. How about now?
Good.
Just the title slide?
Yes.
Terrific. All right. Thank you. And it's my great pleasure to be speaking to you today on this Worldwide Ferry Safety Association webinar on pre-cut vessel design and construction. Excuse me. My company has been doing computer lofting and advanced vessel construction support for ever since we've started the company in 1988. And over that time, certainly the software and hardware has changed. But the basic thinking about pre-cut boats and the advantages that they bring to a build environment have only been reinforced and remain a great opportunity for people to look at as a way to improve construction and facilitate the quality of the build. So today I'm going to talk a little bit about what is a pre-cut vessel, how do the what advantages do they offer? What are the challenges to the designer in designing for this technology? A lot of discussion about build strategy and what makes things better to build. And this is certainly not a new idea. The notion that you can basically have everything other than the labor be ordered online and delivered to your doorstep is a reality. But folks have been doing it for a long time. One of the examples is the MV Liemba, which was built in 1913 at Meyerwerft in Germany. After preliminary assembly, the 71.4 meter vessel was taken apart and shipped in 5,000 boxes loaded on 3 cargo vessels to Dar es Salaam. From there, trains carried the boxes to Kigoma on Lake Tanganyika. So it has been done and brings advantages, especially in remote locations where that may lack facilities or supporting infrastructure to build a vessel. So the kit boat is very much a tool in the toolbox. So what's a pre-cut vessel? Here is one definition that I pulled together. Using computer technology to build a 3D structural model that can then be translated into two-dimensional pieces. These are then cut by numerically controlled equipment to create parts for accurate assembly into a vessel. The focus of this talk will be on structure, but pre-cut could also apply to piping pieces, railing, foundations, etc. One of the ways to think of a boat is a builder already purchases assembled items such as a generator set, a doorway, a control console, etc. So when you're looking at building a vessel, the question of what to manufacture or build yourself and what to buy is very much a part of the planning and thinking process. Items that you are buying obviously will cost more, but they can certainly offer advantages. So what kind of advantages? Well, certainly using pre-cut parts gives you greater accuracy. The computer captures complex shapes, allows you to detail cutouts for stiffeners, lightning holes, even doorways, windows. So the ability to have an accurate set of parts is greatly enhanced with this computer technology. Another real advantage is it gives you reference and part marking. You can actually put on your pieces lines for bulkheads, for where to place stiffeners. You can put on part numbers. You can show which direction to tow the angle or the piece of member towards. So a lot of information to help facilitate the build for the worker. Clever use of NC cut pieces should result in a reduction of parts. Part of the goal is to think about how do I eliminate pieces, because every piece I can eliminate is one less piece that I have to weld. It's a piece I don't have to keep track of. It's a piece I don't have to inspect. So thinking about how can I use cut parts to eliminate smaller assemblies is part of the key. And finally, if you think about it, you can create parts that are self-aligning or allow the use of jigs. If you think of slotting a frame so that a longitudinal member can fit down in that frame in the exact orientation that you want it and be ready to weld, makes it a lot easier. The corresponding, you can also use the NC cutting to create a jig that would allow you to capture, say, a shape of a deck or support a complex part while you're assembling it. So it can not only be used to manufacture the parts, but it can also be help with some of the tooling to help assemble parts. And the NC technology can apply to not just plasma burners for steel, but high-speed routers or even lasers working with other materials. So as a designer, we need to start thinking about how the vessel will be built right from the beginning. By choosing wisely, we can help to make the work of the builder easier. So save labor by working smarter. Some examples of design considerations are shown by this profile of a simple 37-meter double-end ferry. First thing is the hull shape is fully developable. Now, what developable means is if you think about laying a sheet of paper onto something, paper is very hard to lay onto like a ball or a compound surface. It will need to be folded or bent to make that happen. Whereas with a developable surface, the paper will lay on it because it's only got one direction of curvature. And that helps make applying steel shapes to a hull much easier. So certainly encourage anyone who is building a vessel from pre-cut parts is to have your designer create a developable hull, not a compound or complex hull. Things that are traditional in ship design, such as shear and camber, are there for a reason from a seagoing standpoint, but they are also often difficult to build and shape into the vessel. So think carefully about when and where you truly need that. In the case of this ferry, there is no full-length shear or change in curvature from one end to the other. What you're seeing on the outboard profile here is that the shear of the main deck is straight on center line, but there is a camber or curvature to allow water to be shed. So that results in a slight, what looks like a shear at the deck edge. But the decks above are absolutely straight and square and easy to manufacture. Note also that there's a standard 600 millimeter frame spacing from one end to the other. By having a standard structural module, it allows you to think about how do you align bulkheads, how do you provide structural support to your upper portions of the vessel. And that structural module can very much be your friend as you look at placing machinery and content inside the vessel. So the shipyard receives a design and then starts thinking about how are they going to build it. And a vessel is made from thousands of parts, and each one represents choices on how to best to build the boat and how to communicate that information to the people who will be doing the work. One of the examples that I like to look at is if you've ever seen how Lego, which makes the little plastic bricks, they do a wonderful job of packaging up their large kits where they create them into subsets, or if you will, modules that are small in scale. They've got very clear instructions showing how the pieces go together, and they use color in their illustrations to help understand how things need to be flipped or turned to make them go together. On a larger scale, this illustration shows an isometric view of a deckhouse assembly for a barge. Not quite a plastic brick, but similar. You notice that every piece is numbered, that some of the openings into the deckhouse are going to be pre-cut, whereas other openings, such as pipe penetrations and things, will be done afterwards or on site when the piece has been installed. By using isometric views like this, it makes it much easier for a worker to understand how the pieces go together and where the part that he is working with or she is working with may fit into the overall assembly. And again, this goes back to the whole discussion of a build strategy. As you think about how do you put the pieces together in what order, that becomes a fundamental aspect of the whole build. And I'll talk about that more in just a little bit. Another item to consider is what's the availability of plates and shapes for use in building this pre-cut boat. Structural optimization says that you could have different plates that are, one may be 6 millimeter, one may be 7 millimeter, maybe a 9 millimeter. But to the worker out in the yard, it's pretty hard to distinguish between, say, a 6 millimeter thick part and a 7 millimeter thick part. So trying to think about not necessarily optimizing structure, but think of the builder, the worker in mind, is maybe we'll use a 6 millimeter plate and maybe an 8 millimeter plate to make it a little easier for people to measure and determine that, yes, they are using the right thickness of piece. And finally, whenever you're working with structure, you should always be thinking of how is it going to integrate with the outfit. How are the piping, electrical, ventilation, and people going to get in and out and interact with this throughout the build, not just at the end when the vessel is finished, but you've got to be thinking about how is a welder actually going to get in there and weld a keel section or an inner bottom. So you need to be thinking about that human aspect of manufacturing. So I've mentioned build strategy a couple of times. It's planning for success. It's understanding what are the capabilities of the yard, what are the skill of the workers, what kind of lifting equipment is there. That may determine what size modules or vessel you can build and launch. Understand the accuracy of your fit up. Do you have the ability to work with tight tolerances, or do you need to have your tolerances a little looser in order to get alignment and having the parts go together? Can you form plates? Is there any kind of bending capability or forming capability? Or is it going to have to be done with concrete blocks, come-alongs, and clips to help cause plates to lay where they're supposed to? Are there project schedule constraints? Are there something that is driving a particular aspect that you may want to either subcontract work out or have things pre-manufactured elsewhere? Long lead equipment is certainly driving build times in this day and age. So having a good understanding of schedule is vital to putting together the build strategy. I've mentioned make or buy decisions. Do you yourself manufacture the mast, or is that a component that you can have a subcontractor put together for you and not take up your yard space and workers and resources to do? So a good build strategy is holistic with all the parts of pulling a vessel together. It understands tying into schedule, resources, your cash flow can often dictate your build schedule. Can you rent equipment to get things done that you may not need all the time? Things like man lifts, even up to dry docks, are part of the question of your build strategy. So as you get on in your careers and you understand how boats are put together, it's always interesting to understand there is no one right way to build a boat, but there are a number of wrong ways to build a boat. So here's an example of a 80-meter factory trawler, and a very complex vessel, but it points out a number of build strategy questions. For example, the bulbous bow in this case. This bulbous bow is most definitely not a developable surface. So it's going to require special skill sets to have the steel plating shaped and formed to make that bulb come together and work. So is that within the capabilities of the yard, or do they need to have someone build that for them and deliver it to them on site? You've got the engine room is going to be densely outfitted in this vessel with machinery, piping, wiring. How do you schedule that? Do you want to get started on that engine room block first, since it's the one you're going to be working on the longest? Do you want to leave the ends of that block open so you've got access to put pieces and machinery in before you start joining it up with other structural blocks? The quarters accommodations on the boat are going to have different outfitting requirements than the machinery spaces. Higher up in the boat, lighter construction. Is that something that you build separately and drop on later? Or, pilot houses are a great example of something that can often be manufactured separately and be fairly well put together before they're lifted up and put on the vessel. So always be thinking about your build strategy and how are you going to pull the components together. And it doesn't need to mean that you need to build it in modules, but modules can be an effective tool to facilitate production. And here's an example of some modules. This is from a project from many years ago. It was this was about a 70-meter tuna seiner, a very shapely hull. And you can see that in the upper right corner, there is the inner bottom section of it, and it's being built upside down. And the reason for this is that the plating on this inner bottom requires a lot of downhand welding to get the weld seams together. So by building it upside down, it's much easier for the welders to get good weld quality on those plate seams. But then you also see a module on the left that is part of the stern frame, where the shape of the aft end of the hull is beginning to come together. It's got a number of pieces that need to be aligned and supported. Not necessarily conducive to building upside down, so they elected to build it upright with supports, and you can see they're just beginning to wrap a piece of steel plating on this stern section. I always encourage people to think about what's going inside. This is a picture of a offshore supply vessel, about a 60-meter boat. And the 3D modeling here shows all of the bits and bobs that are going in, from the pressure tanks for holding mud or cement, lots of piping, bow thrusters. So as you're thinking about your build strategy, be thinking about, do I need to leave access areas so that I can drop an engine in later when it arrives? Or do I need to leave part of the boat or part of the structural off to give my people the ability to get in and do their work in running piping and wiring and ventilation? So always be thinking beyond structure to the actual outfitting as you're doing your planning. You know, here's an example of, at the end of the day, what a pre-cut part is about. In the middle, you have the computer design of a section of a boat. From that computer design, you then break out a piece that appears in a part of a plate nest in the lower left-hand corner, where it is one of a number of pieces that are put on a steel plate to then be cut, trying to maximize the use of the steel and not have a lot of waste or scrap. But the information on that part also goes into documentation and planning. It can go into a weight estimate. It can go into a production report where you can track your progress on building the boat by how many parts have you used up in the process. It can also be used to help track information on the type of steel in order to satisfy an inspector who wants to be sure that, did you use the appropriate type of steel in building that particular part or portion of the vessel. So a lot of information comes along with the geometry of the cut part. And that information can be very powerful when planning a build project. So as you're thinking about pre-cut boats, keep it simple. Or as one of our fellows likes to say, strive for elegant simplicity. This illustration shows sort of a simplified section of, say, the end of a barge. And it's useful in showing some of the lessons to be learned. If you're going to put a knuckle in a deck, don't put the knuckle right on top of a bulkhead or a frame. Offset it some so that you've got a good, clear plate seam to make that connection to. As much as possible, try and round off your dimensions. Don't let the person try and understand, is that, you know, why did you make it 21 millimeters, rather than taking it up to the next easy number to be able to look at on a measuring tape or a scale. If you're going to use rolled plates and things, help define the tangents and the curvature so that they can then again be checked and verified in the yard. Try and make it simple. Look at understanding the actual production process. Steel plates, when they come out of the mill, are of nominal sizes. Here in the US, they're typically either 8 feet wide or 10 feet wide. But that doesn't necessarily mean that that plate is truly square or true. So one of the things that will be done in NC burning is that they will trim the plate to make sure it becomes truly square. So that will shrink it a little bit, and you've got to understand and allow for, you know, roughly 12 millimeters per side in order to square it up and make it true. So all kinds of thinking about the production when you're trying to lay out the pre-cut parts is important. Don't make your vessel any more complex and is absolutely needed for the service it's going to be put into. This illustration shows two different approaches to doing the end rake of a barge. The upper one is using all stiffeners with transverse frames that are then clipped or bracketed to the stiffeners. And it's got a plate on the right-hand side that forms sort of a headlog for the barge. One of the real challenges is trying to roll stiffener shapes. They can be very difficult to roll and get true. Another thing is that you count the number of pieces that are here, and there are quite a few pieces that are going into this assembly. So can we reduce piece count? Can we make it easier to manufacture and simpler to weld? So instead of having rolled shapes, we now have in the bottom view, we have a cut part that forms the stiffener backing up the shell plate on the bottom. You have another cut part that forms the headlog and has a large limber hole in it so that people can get in and around and weld there. But it's reduced the number of pieces that are used in the construction. So lots of tips and tricks when you start getting into this with an eye towards how to make things better to build. I'll give one more example here. This again is of a barge construction. We tend to think of barges as big steel boxes, but there's lots of nuances in thinking about how they go together. And the secret in building a barge is how do you move steel quickly? How do you get folks to weld and assemble as efficiently as you can? So again, contrast between two sections, the one on the left, the one on the right. What are the differences? Some people might notice that one of the differences is that the one on the right is using bulb flats for the structural members rather than just a flat bar or straight. Bulb flats have better structural properties. They retain paint better because you don't dealing with that sharp, hard edge of a flat bar. And so a lot of shipbuilding industries have shifted to bulb flats because of these advantages. You also notice that the bottom seam is different between the two. In one, the flat bottom plate is on top of the rolled section in the corner. And on the other one, the rolled section in the corner is sitting on top of the flat plate. What this reflects is the build strategy was to build that side piece turned over on its side and then lifted up and rotated 90 degrees into place so that by creating the lap on the right-hand side, it gave them a spot to rest and align that side module on top of the bottom module to make it easier to hold in place and then weld and support during construction. So be thinking of sequencing as you're putting a kit boat together. So other structural issues to consider. I mentioned reduce the number of different structural members and the need to be thinking about how are you going to get someone in there to actually weld. It seems that every shipyard that I know has one welder who is a small person that has the ability to get into the really tight spots to make those welds. But that's not really something you can count on, and you should do your best to try and avoid that. Are the details that you're showing on your plans sufficiently clear and well dimensioned so that people can check it when they're out in the yard? It may seem fine to you sitting on your computer screen, but when you realize it's going to get translated into a piece of paper on a clipboard that your inspector or your supervisor out in the yard is going to be using, be thinking about what they can see and what's easy for them. You can see in the illustration here is a fairly simple hull shape coming together. In this case, they're building the whole vessel in one piece, building it upright. They've laid some of the side shell plating on and are beginning to pull the bottom plating into place. So here's a great example of how pre-cut parts are coming together to build a small vessel. You also note that they've got a cover over things. In countries where it is hot and rainy, your ability to do your work undercover makes a big difference in the productivity of your staff. So always be thinking about how can we shift the work or do the work in a better work environment for the employees. So a quick review, better to build means safer, faster, less expensive, easier to build. Reduce parts. Design the boat as if you were going to have to build it yourself. Pay attention to what's under the structure, behind the bulkhead. How do all the pieces come together? Can you use structure to not only hold out the water, but can it also be used to support a deck fitting or a piece of equipment? Always carefully review the notes and material specs. They're there for a reason. As engineers dealing with regulatory agencies, we put things down on a drawing because we have to, and ignore them at your peril. And finally, when you're pulling a vessel together, don't assume that the part is wrong. I remember on one project, we had a shipyard that was convinced we had mislofted the part because it wasn't fitting nicely the way it was supposed to, and they went ahead and trimmed the part, and then only later came back and discovered that one of their staff had misaligned another piece, and so the spacing was off, and so therefore the part that we had designed was correct, and that by cutting it to fit, they had created other problems down the road. So double check, triple check your work to make sure it's the welding's been done properly, you're not having weld shrinkage, the alignment is correct, and in some projects we found that the time of day where you take the measurements of alignment can make a big difference, because a steel assembly sitting in the sunshine will change dimensions if it's hot out. So the keys to success of using pre-cut parts is allow time to develop your build strategy. Build it first on the computer to identify problems and possibly to see some opportunities. Pull the information together in a package that is easy for folks to use when they're building it together. And small errors can grow into big problems, so catch them early. If every stiffener on a plate field is misplaced by 1 millimeter between them, and you've got 20 stiffeners, that means that the last stiffener is going to be 20 millimeters out of place, and that's a big error. So catch them when they're small. And so finally, questions. We got some questions in advance. And I don't know, Richard, if you want to take it over at this point and be the Grand Inquisitor.
Okay, I'll start by asking some of the questions that have been submitted. The first question had to do with the definition of pre-cut or modular, and I think you've discussed this in the presentation, but I think there's probably something we should discuss about it even further. Pre-cutting structural or other outfitting parts. That does not prevent one from adopting a modular approach to vessel construction, does it?
No, I mean, modular can be a portion of a pre-cut boat or not. That goes back to the discussion of the build strategy. And you can build a modular boat and not use pre-cut parts if that is your choice. There's no reason why, in my example of building the deck house separate from the rest of the boat, there's no reason why you couldn't build a deck house and then lift it on and go ahead and trim the pieces to fit if that was your approach.
So it seems to me there's a kind of a hierarchy in the design approach here, where first of all, you're designing for the mission of the vessel, and then you have to consider the design in terms of the build strategy. And that would lead to actually doing the details of the lofting for pre-cutting the members of the vessel. Does that sound right to you?
I'm sorry, could you state that again? I'm not sure I followed that.
I'm saying there's kind of a hierarchy here, where first comes, you're going to design the vessel for the mission of the vessel. And then secondly, you're going to take that design and you're going to you're going to change it or redo it in terms of the build strategy, whether you're going to do it modular or partly modular or whatever. And then lastly, then after you know what the build strategy is, and then you know that it satisfies the intended mission of the vessel, then you're going to do the lofting and do the pre-cutting.
Yeah, I mean, obviously it depends on how the project goes forward. Often we as designers don't know what yard is going to build our vessel. So our ability to incorporate particular information about a yard is limited. In some projects, we have the ability to work with the yard right from the beginning, and that's terrific because it allows them to introduce their strategy, their thinking, their best practices into our design efforts early on in the game, and that often results in a much better product at the end of the day. But it's never too early to start thinking about how is something going to be built. And we as designers certainly have a responsibility, especially as we're preparing details to be approved by the regulatory authorities, that are our details friendly to the builder or not. A great example is the joint between a deck and a side shell. You can any number of different ways you can join those pieces of structure together. Some are going to be easier to fit up and weld than others. So are you, as the designer, choosing something that is fit for purpose? If you're using an unusual or different detail, it better be for a solid reason related to the mission of the vessel. For example, I've seen details where the deck plate is carried beyond the edge of the shell, and then a half round piece is brought in underneath as a guard. And so that allows a good weld between the shell plate, the deck plate, and the guard to all come together in one spot. But always be thinking about how it's going to be built.
Another question, in fact, it's a pair of questions. It says, is strength analysis necessary? And the second part of the question is, what rules or regulations are used? I think those questions are related to each other. Would you like to comment about the regulatory aspects of this?
Yeah, clearly, regulatory is determined by your customer. Who are you building or designing the vessel for? Um, that customer will have requirements that they either need to get approvals from the local safety authorities, or they need to meet certain standards in order to get insurance to cover the vessel. So those will often dictate that a design and construction be done in accordance with a set of regulations. Quite often, those are from a classification society, and classification societies are third parties in the marine industry that provide a safety standards and inspection role. For example, Lloyd's Register is well known as an inspection as a class society, as is the American Bureau of Shipping or Det Norske Veritas. So we will design to those standards as part of a process. And those standards will often require structural analysis of some things, or they have prescriptive formulas that you plug values in and calculate required thicknesses or section modulus of materials that come out of it. So it's structure is usually a pretty well prescribed process. We will sometimes get into exotic stuff, or we'll turn to modern tools such as finite element analysis to determine not just strength levels, but also perhaps vibration and impact loading responses to things. But for the most part, our design work is wrapped around fairly prescriptive rules from the classification societies.
And then another question is, what facilities are needed for pre-cut and modular related to the local shipyard?
At its most basic, you need an area to receive the parts, lay them out, and be able to access them when you need them. You generally need some kind of open, flat area with good support underneath. So as you're building the vessel, it won't sink into the sand or tip over as weight is added. So looking at what your building area looks like. And you've always got to be thinking about, how are we going to launch it? How are we going to get it into the water? Is that something that we need special facilities to do? Or in this day and age, can we use airbags or logs or other means of getting things into the water? So I've seen everything from a sandy area on the bank of a river to very fully developed construction facilities that provide climate controlled environments for people to put things together. And the latter is more typical of aluminum boats, because aluminum welding requires a different set of skills and is more environmentally sensitive than steel welding is. And so that's why you'll often see aluminum welding taking place indoors, or aluminum vessel construction taking place indoors.
We're going to run out of time here in a few minutes, and I'd like to give our participants a chance to ask some questions. If you're interested in asking a question, could you please raise your hand in the I don't see any hands coming up here.
Richard, it's because we asked the students to kindly submit their questions in advance.
Oh, okay.
Yeah.
Okay. Let me Here we go. Um,
While you're looking, Richard, one of the questions that came in is saying, with this method, the pre-cut design, is it possible for the manufacturing process of ferry boats to be conducted in different locations? Module fabrication process carried out in external yards while the assembly is done in a location around the Niger River. And the answer is absolutely. There's no constraints. You could have the vessel prefabricated in parts that could be loaded on a truck and driven to the river site for final assembly. And that's often done in, as he said, remote locations. I remember seeing.
I've also been involved in moving structural modules by barge to the assembly site.
Yep.
And that works pretty well too.
Yep. I remember seeing Washington State fabricated a ferry for the Columbia River, and they moved it in 3 large sections over the highway, distance of a couple of 100 miles to get it to where it was going to be final assembled. And so in my earlier example of the steamer on Lake Tanganyika, anything is possible.
Okay.
Well, if I could jump in, I have to say that I think this presentation exceeded all expectations. It was tremendously comprehensive, and maybe, thank you very, very much, John. Richard, do you want to say a few words why this topic is near and dear to your heart?
Sure. I was involved in a project, this was some years ago, but I was involved in a project in Haiti. And Haiti is a fairly mountainous country and road transport is very difficult. And we were, but Haiti also enjoys a very long coastline. So we were working on a project to provide transportation by water, which would include water taxis. It would include vehicle ferries, and also some basic coastwide shipping. And one of the things that after having visited East and Central Africa, became aware of the kinds of things John alluded to on Lake Tanganyika and Lake Victoria. And we were thinking about, I'd asked the rest of the faculty to consider the implications of doing kittable designs, where we would pre-cut all the parts and pre-outfit. We would have all the piping and wiring and so forth kitted as well. By my calculation, this would have fit into 2 40-foot containers. We could have then transported the containers to Haiti. There were skilled mechanics and welders and so forth available there, but they had no marine experience. But they were perfectly capable of doing all the work, as long as somebody with marine knowledge was able to supervise it. And this plan was, at the time, very attractive to the Haitian government. And unfortunately, things there have not gone the way we had hoped they had gone.
Okay, thank you. We're going to, again, I'm astounded. We did a great job, John and Richard. John, wonderful presentation. It's now going to be on our YouTube channel. I'll make the recording available to all participants. But again, thank you very, very much. Let me again conclude by being very happy about this. I think it's exciting, and as technology evolves, it's quite possible this kind of approach will be used more and more. So I'm going to say goodbye, and thank you very, very much, Richard and John.
My
And let's
pleasure.
add my thanks to John. John, you did a great job. Thank you.
Okay, take care, everyone.
Thanks.
Bye-bye.
Thank you. Bye.
Thank you.